it sounds like an attention seeker. This is just the app that's doing this, okay? I have no choice in the matter. So, hello everybody. Very welcome at the course Physics 3002, Theory of Relativity. And I hope you signed up and went to the right room, because just a second ago somebody came in and asked whether this was bio-based biology or something like that. I said yes, and they decided to not take the risk and walk out again, because obviously we're going to talk about relativity. Now, I know a number of you already, but there's also a whole bunch of people that I don't know already. Now, we will sure, of course, get to know each other during the tutorials. Now, for the people who don't know me, my name is, depending on your background, it's either Gideon, that's the Dutch pronunciation, or Gideon. I'm completely used to both of them, so take your pick, or any combination thereof. I'll be happy to listen, as long as you keep it somewhat decent. We are going to talk about space and time in the next month and a half or so, namely the theory of relativity. Now, I'm not going to do this all by myself. Over there you have Brecht. He's waving right now. Brecht is our PhD candidate, and he's going to be one of the other tutors. We have 4 tutor groups. Brecht is going to take 2 of them, the other 2 will get me. And in the tutorials, obviously, we're going to talk about some of the cool exercises. You might notice that I installed this gizmo thingy over here. That's new to me as well. Okay, so this is why I had to tinker with the thing a little bit, because I had to get used to it. Because I'm one of those people who don't use slides. I do everything on the spot with a marker on the board. The reason that I do that is because in physics you derive things. If I just show you slides, this is true, click, by the way, this is also true, click, and by the way, this is also true, click. Sure, I'm sure you get everything nice on one slide, but I like to keep the option open to derive everything, so you see how it's done, that's one. But secondly, that also means that you can decide whether you want to focus on the derivations over here, or you want to take down notes. Now, if you're going to make one of those 2 choices, you're either going to write down notes, but then you might miss what I'm saying, or you decide to listen what I'm saying and you might not get everything right. This is why I record this. So this will be uploaded at the end of every lecture day, so by tonight on Canvas. And because I have money to spend, more money than I decided to keep to myself, I said, you know what, instead of just putting here a camera that is static, that's how I used to do it, I bought this thing, and well, we'll just have to see. Well, look how cool that thing is. It sort of turns me around, okay? It's also a little bit creepy. So I honestly don't know how well it will work. We will find out as we go along. But this recording you will get. And again, that means that you can decide whether you want to follow me on the board and all the derivations, or that you say, you know what, I'm going to focus on the physics, the narrative, the story, and then maybe you can pick up whatever you were missing with the recording later. Yes? So again, no slides, but nice local derivations. Also, that means if you have a question on something, that means you want to ask it, that means we actually have some space that we can actually do this on the spot. I would really hate it if somebody said, oh, by the way, I have a good idea. What if we tried this and that? And I said, well, you know, that's a good idea, but I don't have a slide for it. So it sucks to be you. I'm going to do my own story anyway. Okay, I want to keep the discussion as open as possible. So all reasons why I do this on the board. Again, Brecht over there and myself are going to do this course with you, and I propose that we just get started. And just out of pure interest, who of you has some background in relativity? Be it small or so. Brecht, you don't count, okay? Some people do. Is this high school background or something else? Yes-ish, yes? So, I'm not quizzing anyone, but just out of pure interest, what is relativity to begin with? I mean, what is the theory about? Yeah, space and time, I mentioned it, but what about space and time? No, feel free to...
The way space and time change, well, length, I guess, depending on the speed you're going.
Okay. I'm just collecting thoughts. Max?
As we approach the speed of light, what happens to length and what happens to compared to different points of view?
Okay, sure. Still collecting thoughts, yes?
Yeah, I just wanted to add that it's we're watching between 2 different inertial frames.
Okay, inertial frames, first time we heard that word. Anyone else? Without quizzing, I just want to make sure on which ground we're starting. Okay, well, we have enough to go on. So what I heard was, well, it's a theory about distances, lengths, right? So the distance between one point and the next, but also it's a theory about duration, as in the amount of time between one thing and the next thing. Yes? And those numbers are different depending on who you are. And by who you are, I don't mean your personal preference, songs or music or wherever you come from. No, it's dependent on what is called an inertial frame. Now, if this word doesn't mean anything to you yet, that's exactly why we're here. So, what is special relativity? It's a theory that says how amount of time and the amount of distance, so the amount of seconds and the amount of meters between two things are different between one inertial frame and the other inertial frame. Second semi-quiz question. Do people know what an inertial frame is? I see some slight nodding. Yes?
Maybe if I remember.
Okay, no, please go ahead.
I think it's a frame in which Newton's first law applies.
Okay, there we go. So, complete, perfect definition right there. Okay, well, let's start there. Yes? So, what is relativity? Again, just to stop our discussion we were having just a second ago, what is special relativity? It's a theory of space and time, distance, the amount of meters and seconds, duration, between two thingies, depending on which inertial frame you are in. And in a moment, let's indeed define what inertial frame is, because we cannot do special relativity, let alone if later in period 5 you want to do general relativity if you don't know what an inertial frame is. So let's put the words into place first and then we can start to discuss. Relativity, Einstein's theories, comes in two varieties. I already mentioned them. One is called special relativity. That's this course. The other one is called general relativity. That's the course that, if you decide so to follow it, in period 5. They're both aspects of the same idea. Space, distance, and time, duration differ from frame to frame, from observer to observer. The difference between this one and this one is that this one only holds in, the word was already mentioned, in what is called an inertial frame, to be defined in a moment. So an inertial frame is just a coordinate system. Right? Suppose an x, y, and z coordinate system. But the inertial frame has special properties. We will discuss that in a moment. You also have coordinate systems that are non-inertial, again, to be defined in a moment. In non-inertial systems, everything we're going to do in this course will not hold. This is why you have to go to general relativity. So, special relativity only holds in these thingies called inertial frames. General relativity holds, well, in inertial frames, but in every other frame as well. So it holds in all frames, whether they are inertial or not. Yes? That's why it's called general relativity. It holds always. And special relativity only holds in special cases. Which special cases? Well, the case in which your coordinate system, x, y, and z, happens to be of this type. Yes? So, everything we're going to do in the next month and a half or so is all of that is this. This is much more complicated for reasons, if you want to follow the course that we see in period 5. The mathematics is more complicated, the physical interpretation is more complicated, it's also more beautiful. But this is what you get. If you go from the special case to a general case, you typically find yourself in much more complicated waters. Yes? So, only going to focus on this. But again, this is only a useful definition at the moment that I've told you what an inertial frame is. So, what's an inertial frame? Let's start there. The definition was already given, but let me first give you a wrong definition. And I'm going to give you the wrong definition because it tends to be so that the wrong definition sometimes pops up in discussions and sometimes even in some books. So it's very easy to get that wrong. I noticed, by the way, I'm not being tracked anymore. The camera decided that I'm not AI compatible. Let's see if I put my face there. Okay, now it knows that I'm here. Okay, so that's €300 well spent. I don't know what it is. Maybe I'm just walking around too fast. I don't know. Or maybe the thing doesn't like relativity. Who knows? We'll see. Again, this is an experiment. It's literally the first time that I'm trying this, except for my living room last night. So we'll see how well it goes. Okay, let's start again with the definition of an inertial frame. And I'm going to give you the wrong definition first. So if you're going to take notes, keep a red pen at the ready to put a big cross through it, okay? But this is a definition that sometimes people find in books. Here's the wrong definition. An inertial frame is an x, y, z coordinate system that is moving with constant velocity. So coordinate frame or coordinate axes that move with constant velocity. That's a very sucky definition. That's a sucky definition. Am I in an inertial frame according to this definition? Yeah. Well, I'm moving with constant velocity with respect to you, right? The velocity happens to be 0 right now. So if this definition is true, you would say, yes, you're in an inertial system. Yeah, but suppose you happen to be standing on the moon. And then you were looking at me, then you would actually see me move about you. With a non-constant velocity, you would be in a circular orbit or so. Yes, and a circular orbit is not constant. You're not going in a straight line. You're taking a turn. That means non-constant velocity. So all of a sudden, inertial system, whether I am right now in an inertial system with my x, y, z coordinates, according to this definition, is dependent on, well, who are you asking? Are you asking you guys? Then the answer is yes. Or are you asking somebody who's on the moon? Then the answer is no. So that's a crappy definition, because this can then only be answered if you would already point out some other person to ask. That doesn't quite work. Unfortunately, this is a definition that sometimes books try to sell to you. That's a very bad definition. It gets you in all kinds of troubles. Especially if you're going to do an exercise and you have to decide whether you have to use special or general relativity. You get the definition wrong, you get your conclusion wrong, you might be doing the wrong calculation. So again, it's extremely important that we can distinguish the two. This is why I said, well, make sure that you have a big red marker available, because this doesn't quite work. What we would like to have is a coordinate system, or a definition of a coordinate system, such that you don't have to ask the other person whether you are in an inertial system or not. That's the correct definition that I'm going to write down now. It was already mentioned in the back. It's a coordinate system in which Newton's first law holds. That's a correct definition. Do people know Newton's first law? It's from your classical mechanics. If not, it's fine, but we have to keep the words at the ready. Newton's first law, please.
Things don't move unless acted upon by an outside force.
This is indeed how Newton's first law is typically stated. That if you take something, I'm paraphrasing what you're saying, so thank you. If you take some object, like a ball, you place it over here. And if you make sure that the net amount of forces on that ball, the pushing and pulling, by gravity, by you, by electromagnetism, you make the net amount of force 0, then that ball wants to go in a straight line with a constant velocity. Right? It's called the inertia of mass. Thingies like to go straight line, constant velocities, unless you start pushing and pulling on them. But if you leave them alone, straight line, constant velocity. The fact that matter, has this property is what we call Newton's first law. I want to stress this is not a triviality. Nobody knows why things like to move in a straight line with constant velocity. But the fact that it's the case, and that you can identify it as such, that's what we call Newton's first law. And it's this definition, defining an inertial system based on Newton's first law, that takes away the ambiguity between the moon and you if you want to know whether I am in an inertial system or not. Yes? let's do an example to show you that, to drive this point home. Still working, good. Suppose that, I don't know, I take some cart here or so, yes? And I'm going to place my ball, my mass, on this cart. Okay. There's a train track on which the cart can move. Pom, pom, pom. And I'm going to introduce a coordinate system on top of the train cart. So that means there's a position, I don't know, 2, there's a position 3, there's a position 4, 1, 0, so on and so forth. And at the same time, I also have a coordinate system on my train tracks. 2, 3, 4, 5, 1, 0, minus 1, so on and so forth. Yes? Okay. Note that in the way that I drew my situation, on the mass, the ball, there's no net forces. Nothing is pushing and pulling to the left or to the right. Something is pushing down, that's gravity, but then again, the material properties of the cart are pushing back up. Those two balance out, horizontal or vertically speaking, no net forces. So the amount of net force on this ball is 0. Okay. Now comes a twist to the story. I'm going to make my cart move with an acceleration. Now it's independent from my argument here where the acceleration comes from, whether you are pushing the thing or somebody's pushing and pulling or the thing is motorized, it doesn't matter for the story. Okay? Here's a question. There's 0 net forces on the ball in either situations. In the green coordinate system that is painted on the cart, and there's also net zero forces on the black coordinate system. Okay? So, according to Newton's first law, that means the ball should be standing still. If it started with standing still, velocity is 0, and Newton's law says, hey, no net forces, then it should remain in its velocity. It should not accelerate, it should keep the velocity 0. Then I have a problem here, because with respect to which of these coordinate systems is this ball going to be at velocity 0 or remain at velocity 0? It cannot be both. Because suppose that for some reason the ball is decided, you know what, I would really like, following Newton's first law, I would really like to stay at fixed position with respect to the black coordinate system. Okay, suppose that for some reason the ball has decided that that is a system with respect to which it should stay at the same position. Fine. Then in the cart system, remember the cart is moving in this direction, then in the cart's position, somebody who's measuring the position of the ball using the green coordinate system, they will say, well, you started at 2, and a second later you were at 1, and a second later still you were at -1, and a second later maybe you were at -10. Then the person in the green coordinate system would say, hey, wait a minute, in my system I see the ball accelerate. Yes? But both systems, there is a zero net force. So clearly, in one of those two systems, Newton's first law is not upheld. In the example that I took, that the ball wants to stay at rest with respect to the black system, in the green system, Newton's law does not work anymore. It gives you the wrong conclusion. No net forces, yet in the green system you see it move to the back. By the way, maybe it's the other way around. Maybe nature has decided, the ball decided, you know what, I would really love to stay at fixed position in the green system. That's fine too. Hello. In the green system, maybe nature decided that this is the one that it should not accelerate with respect to. Fine. In that case, it will stay position 2, the ball, but then in the black frame, it will go next second to 1, next second to -1, next second to -10 or something. And that means in the black system, Newton's first law is not upheld. No matter how you try to look at the situations, in one of those two frames, Newton's first law does not give you the right conclusion. In one of the two frames, biology, in one of the two frames, Newton's first law gave you the wrong outcome. You cannot have Newton's first law be correct in both. One of them is broken. Now, which one it is, that's a fun exercise that Brecht and I will discuss with you in the tutorials later. For now, the only conclusion is Newton's first law cannot be both true in both systems if those two frames, the green and the black, have a relative acceleration with respect to each other. Okay? And this indeed is where our definition of inertial frame comes from. We are going to call the system in which Newton's first law is upheld, that one is by definition called the inertial frame. So suppose that, as in my first example, that the mass really wants to stay at rest with respect to the black frame, then the black frame is the inertial system. The green frame is not. Yes. Now note, in order for you to determine now whether I am in an inertial system or not, you don't have to ask the person on the moon anymore. The only thing you have to make sure is that there's no net forces acting on me. And I think there are none. Nobody's pushing and pulling, and gravity's pulling me down, force pushing me up, no net forces. Yet I'm not accelerating. Yes. That probably means that the floor is an inertial system. Yes. And if you ask the moon person will look at me and say, hey, wait a minute, that guy has zero net forces on them, yet I see them accelerate. That means the moon person will say, okay, that guy is not an inertial system. Or, excuse me, the moon person will say, in my frame, I can tell that I'm not an inertial system because I see somebody with no net forces accelerating. Yes? This is a definition of inertial systems that has absolutely nothing to do with, I don't know, whether your system is moving or not. You can just check, is Newton's first law upheld? That's all that you have to do. That's an internal definition. You don't have to ask somebody else. Okay. By the way, I was slightly lying when I said, well, the Earth is an inertial system. It isn't. And if you don't trust me, take a mass, string it up on some very tight rope for 10 or 20 meters or so, and watch it go. No net forces, but at some point it will start to oscillate around this plane. Right? It's called Foucault's pendulum. See some faces that have never heard of this? Okay, take clouds. I understand the atmosphere is a very complicated system, but by good approximation, let's say that you have a cloud, and the amount of pressure on all sides is equal, so there's no wind pressures pushing it about, no net force on the cloud, so to say. That's difficult to get in practice, but as an example, let's take that. If you look at the weather maps, you will actually see the clouds not just move, they go into circular orbits, they accelerate. That tells you that if there's no forces on the clouds, yet you see it accelerate, then that their frame must be a non-inertial frame. The Foucault pendulum that I mentioned, you might want to look this up, is exactly that experiment. They take a mass, they put it up on a high string for a few meters. You need a whole lot of meters, 10, 20, 30 or so, to really make the effect quite visible. You just leave it there. No net forces, nobody's pushing, pulling, no wind. Gravity pushing down, string pulling it up, no net forces. At some point the thing will start to oscillate around this plane. Please go to France or Italy, because they have these beautiful Foucault pendulums, literally sum up, you can actually see it happen. That tells you that the Earth is not an inertial system. The reason that you don't see it on me is because I'm not strung up on a big rope, and you don't give me long enough to start moving about. Yes? So sometimes things look like an inertial system because the scale on which you look at your mass is very limited in distance and in time. This is probably why, I wasn't there when you were at your high school, but this is probably why I'm guessing your high school teacher, when you were learning mechanics and Newton's laws, probably never spoke about inertial frames. It's rare that you see this on the secondary school education. It's because usually in high school physics, you typically do your calculations compared to the Earth's surface, which for many practical purposes it's not inertial frame, but you know, your experiments, you're dropping pens, you're flowing balls, you're falling apples, don't drop long enough in time to see the non-inertialness come about. So you never really have to worry about this. But the difference is there, and it's important. Again, if you get the inertial system wrong, and you can't do your mechanics, Newtonian mechanics on this, you're going to get the wrong conclusions. Suppose now that in addition I'm going to start pushing and pulling on the ball by either my own forces or because, I know, electromagnetism, there's wind blowing or whatever. If you get this wrong, let's make the black system the inertial system, and let's make the green system the non-inertial system. And you're now one of these people using the green coordinate system to track how this ball is flying. Well, you would use Newton's second law, right? F equals m times a. You plug in your F, you do a calculation, then you can calculate the A of the ball and see where it should end up and everything. Yeah, but if you were never in an inertial frame, Newton's second law is also going to give you wrong conclusions. Because you're going to get accelerations that are there because you are in a non-inertial system and not because there's a force acting on you. Everything becomes messed up. So it's not just that the inertial frames defines when you get to use special relativity versus general relativity, it also tells you whether you can use Newton's laws to begin with. So special relativity and Newton's laws, they're different theories, but they come with the same criterion. Both of these only work in inertial systems. You really have to keep that in mind. General relativity says if you want to track how things are going, space, time, moving masses, but you want to do it from the green system, in our example that's a non-inertial system, then you have to use general relativity. And then things become, well, unfortunately, mathematically more complicated. Also more beautiful. But I have to go attest to it. Okay. Yes? All right. Good. With all of that said, we now know in what domain we can use all that. We're not going to use this anymore. In the tutorial, Brecht and I will discuss a little bit with you how one can define or how one can determine inertial systems by experiments. And that's a fun exercise to work on together. Okay, good. Now, I've mentioned no relativity whatsoever at this point. I simply said you have to make sure that you can keep the two frames different from each other. In every single one of our lectures from this moment on, we're going to assume that we are in inertial frames unless otherwise specified. Yes? Okay. Also holds for the exercises. In all exercises, they typically say, oh, something is flying in this direction, and check how many seconds happened in this frame versus that frame. You can assume that all of them are inertial systems unless otherwise specified. Okay. Okay. So let's start with relativity proper. When I asked before, people put up their hands and said, yeah, I know, I've seen a little bit of relativity before. Can somebody give me, it's not a quiz, I'm just simply curious, can somebody give me a starting point for relativity? Right? Relativity came about in 1900, slightly later. Einstein came up with it, although there were many physics experiments and physicists already aware that something should be up with space and time because otherwise the rest of physics didn't make sense anymore. And Einstein was the first person who saw through it all and was able to write down everything of it. So, does anyone know? Yes?
Speed of light is always constant.
Sure.
Or invariant.
Yeah, let's use the word invariant. But thank you. I'm collecting thoughts now. Anything else? Other starting points of relativity that you happen to know about?
Time dilation.
Time dilation, sure. That people notice that some amount of time here might not be the same amount of time over there. There were experiments that were telling this, yes? There was something up with physics. It was Einstein who came up with the full definite use. Have hand up?
Yeah, there's also the Lorentz contraction, right?
There's also Lorentz contraction, agreed. That means that space all of a sudden became stretchable. All of that was measured, but not understood. And the last thing people did when they measured something and they say, wait a minute, it used to be a meter, now it's 80 centimeters, but now it's a meter again, so something is stretching. The last thing people thought was maybe it's space itself, because space is just space, a meter is a meter, right? They thought it was materials that had these special properties. No, it was space itself, and the same with time. Yes?
Is this the example with the spaceship, Einstein? When the laser in the spaceship goes off course, or is that later?
Yeah, no, that was how Einstein in his didactics showed it.
Well, yeah.
Let's go the Einsteinian route. What we're going to do in this course, do a derivation of special relativity in two ways. today is going to be the first, the historical way. That's the speed of light way. Yes? We'll walk you through it in a moment. Since then, people have figured out that actually relativity can also be completely built up without having to do the historical way. That is there's a much deeper rule to it. That rule we're going to see next week. So we're going to do sort of the historical one this week. That's the one you would typically find in the books. That's the one with the laser lights, etc. And the next week we will see that there's actually a much deeper rule attached to this. And foreshadowing, the deeper rule again has to do with the with the inertial frames. You'll see that next week. Let's do the historical one first. Okay? Let's go to late 1900s. Late 19th century, so late 1800s. Okay. The big thing in physics back then was electromagnetism. Thermodynamics also, by the way, but for our story we are going to use the electromagnetism. People had figured out in the course of about 100, 150 years that there's a thing called the electric field. Bless you. This thing called the electric field that tells charges how they're being pushed and pulled around. If you have a plus charge over here, you have a minus charge over there, they start attracting each other. If they happen to be the same charge, minus and minus, they repel. Plus and plus also repels. Yes. That was figured out, and people decided that the thing in between that tells the one charge plus to the other charge, you should move away from me now because we're of the same kind, that thing in between was called the electric field, called capital E. Yes. We're not going to delve too deep into the details of electromagnetism. I'm simply telling you that this is the state of affairs because this is how we got Einstein relativity, historically speaking. But people had also figured out that if you had a magnet, some rocks had this property, that they also start pushing and pulling on each other, despite not being charged, despite themselves not having a plus or a minus. So, if you have a magnet, and you have another magnet, then these two push and pull on each other, and that thing is called a magnetic field, and they call it capital B. There's a little arrow on top, because an arrow in my notation means that there's a direction to it. Right? These two guys are pushing each other in this direction, and these two guys are also pushing each other in directions. That's what the arrow means. Okay. This was 1800 or so. Later, people figured out, but wait a minute, the electric field, the stuff that tells charged particles they should move about with respect to each other, and the magnetic field, the stuff that tells magnets how they should move around with respect to each other, are actually connected. Electric fields and magnetic fields are related to each other. Now for us that's not new because we constantly talk about electromagnetism. Back then was completely new. People had no idea that was the case. Those were famous experiments, right? That Oersted, for instance, scientist, Danish, did a little copper wire and it was filled with electric charges. And when he made the charges walk, so all of a sudden the charges went from this side of the copper wire to the other, he just put a current through the wire, then a magnet that happened to be next to it all of a sudden started to move about. But wait a minute, there's no magnet around. So Oersted figured out, wait, if I have an electric field, because that's what the charges in the wire have, but the electric field is moving, because that's what you do if you give it a current, you make the particles move and therefore the electric field moves, then it behaves as if there is a magnetic field, even in the absence of an actual magnet. You can turn electric fields by moving them about into magnetic fields. Right? We call this induction now. You can also do it the other way around. If you take a magnetic field and you make it move about, then it behaves as something electrical. So you can turn this guy into that guy. If you wobble this guy around, you get this guy back. If you wobble this guy about, then you get that guy back. If you want to study more about this, that's the course of electromagnetism given by my colleague Benedict Poser. Yes? We're not going to delve too deep into this. In the notes that I will upload by tonight, you will see a little bit more derivation for the people who want to connect it to the course that you might already know about electromagnetism. If this is not you, that's fine. You don't have to memorize this. Just focus on the qualitative. Here's the qualitative part. At some point, people were able to connect all these connections, so to say, between electric fields and magnetic fields into one big theory that we now call electromagnetism. Again, that's the course that you can also study here. For completeness, I will write down the equations. These are called the famous Maxwell's equations. They were written down by James Clerk Maxwell. This is the later half of the 19th century. And these are the equations that came out. Again, don't memorize these, different course. But I can tell you what they tell you. This symbol over here, it's called divergence, it tells you how much this field, the electric field, is sticking out. Right? If you would assign to this field arrows that tell all particles where to move, then this symbol says, well, in which direction do the arrows point? If you look at the magnetic field, it says the arrows actually don't point anywhere. They're zero. Well, that either means that there's no arrows, or that every arrow that tries to stick out also tries to stick back in. So the net effect of sticky outiness is zero, so to say. That's what this law tells you. So the magnetic field lines, as we say, are closed. That's what the second law tells you. This one tells you that electric fields, they're not zero, so there is actually a net amount sticking out. It says that particles, their electric fields, radiate electric field like a sun, in every direction the same amount. That's what this guy tells you. Okay? Here things become more complicated, but also where relativity starts, historically speaking. Namely, this symbol, there's a cross instead of a dot now, says how much an electric field is rotating around, whether it's a straight line or has a rotation to it. And what does it say? It says if your magnetic field, and you take its time derivative, that means you make the magnetic field not constant, but you shake it, you will get back something that resembles an electric field. This is the induction step that we were talking about before. This is how they make electricity in turbines. They take a big magnet, they make it rotate about, maybe because there's water flowing over it or something like that, right? With a waterfall, they put a big magnet on top of it, the magnetic field will turn around, that's this number. You get back the electric field, and that they bring to your socket, and you can charge your phone. That's this effect. This effect is the other way around. It says you can make a magnetic field either by having a current. That was what Oersted found when he had a copper wire and he put some currents through it. Right? He saw his compass move about. That's this effect. But you can also make a magnetic field by time derivative, taking an electric field and shaking it about. If I take in my hand over here a charged particle, like a proton, and I shake it, then this is not zero, that means that is not zero, and I get back an magnetic field. Yes. So in other words, these two Maxwell's equations tell you in which directions the arrows point of electric fields and magnetic fields. These two tell you how much you influence each other, that you can turn one of them into the other. Okay, then Maxwell, I'm talking about the guy now, asked himself the following question. He said, okay, well, let me start with a charged particle, like a proton. By the way, he didn't know about protons, but let's use our terminology. That if I now take a proton and I start shaking it about, then this equation tells you you're going to get a magnetic field. But since you're shaking about the electric field, the magnetic field is also going to be shaking. But then this law tells you, but wait a minute, a shaking magnetic field gives you back an electric field. So I started with this proton with only an electric field. I shake it about. I get a magnetic field. That guy shakes about, but wait a minute, that gives you an electric field. But then this guy tells you, oh, but then you get the magnetic field. And then that guy tells you, oh, but you get an electric field. And then that guy tells you, you get a magnetic field. So you have this constant turning of electric fields into magnetic fields, back, forth, back, forth, back, forth. That's a direct consequence of these two laws. Yes, I'm not going to ask you to calculate this for me, but you can see from the equations that that's the case. This is what was figured out. And then Maxwell, again, the guy, he asked himself, okay, well, this shaking about of electric to magnetic, what does it do? Does it just stay in place? The back and forth of electric to magnetic, back, forth, does it stay here, or what is its dynamics? And it turns out that if you do this mathematically, I mean, the notes that you will get by Canvas by tonight, I show you the calculation in case you're interested in the details, you will find that the magnetic field, excuse me, let's take the electric field, that the electric field second derivative, the electric field, there's a mu 0, epsilon 0 over there you go. Now, again, if you don't read mathematics, don't worry about it. Let me tell you what it says. You take these two together, you're going to get this equation. That's a very famous equation from physics. It's called the wave equation. It tells you what the electric field, the net electric field of this shaking about, what it does in space and in time. It tells you how it moves in space and then how it moves in time. And the solution to this equation is a wave, is a sine. Something that goes up and down, up and down. The electric field goes up, it goes down, it goes up, it goes down. And it tells you how fast it actually moves through space. So the shaking about of my electron here goes to magnetic, back to electric, back to magnetic, back forth. Doesn't stay in one place, it travels. And it tells you how fast the traveling goes. The traveling happens to be a combination of these numbers. And the number that came out, so that the velocity of this electric magnetic shaking, if you plug in the numbers that people already knew from having done a century of experiments on electromagnetism, the number came out 300,000 kilometers per second. So Maxwell theoretically calculated that. And he was super surprised because, well, the number was known. There was a known number. It's the speed of light. Further way back still, this is 17th to 18th century, people had already measured how fast light goes. They had no idea what light was, but they could measure how long it takes for light to go from here to there. Yes, they have all kinds of ingenious experiments to do that with. So they already knew this number. So Maxwell, not having to do anything with light, he was just interested in how electromagnetic fields talk to each other, how they turn into each other, did the calculation, found, wait a minute, my electromagnetic wobbling is traveling through space as a sine, up, down, with exactly this number. So there's a famous letter that Maxwell wrote to his friends, and I forget the exact quote. It was a Scottish version, so I wrote it in English, but it translates to, I've accidentally found that light is nothing else than the wobbling of electromagnetism. We know that. We call light an electromagnetic wave. But somebody had to figure this out for the first time. Nobody knew what light was. Maxwell found it. That was a big discovery. Now, Nobel Prizes were not given in those days, but he would have gotten it for that discovery alone. That a thing, electricity and magnetism, unrelated to each other, turned out to be related by these two equations. And when you combine these two together, you also find light. All of a sudden, everything in physics started to get connected to each other. Big discovery. Okay, but where's the relativity in this? Again, we're still being historical here. We're now at the end of the 18th century, beginning of the, I was messed this up. 1890s, thank you, Beth. Starting of the 20th, thank you. Physics, easy. Counting, difficult. 20th century. This was a big discovery, but here's an interesting thing. Going from here, Maxwell's equations, to this wave equation that tells you that the solution is a wave that travels with this velocity, you never, ever, ever in this calculation have to say with respect to what you were calculating this velocity. The number apparently comes out without saying, well, I'm measuring it with respect to, well, the green or the black frame. It comes out the same always. That's a little strange. Normally, if you calculate how fast things are moving, you first have to define, well, am I measuring it with respect to this coordinate system, or some other coordinate system, or the coordinate system on the moon, or the coordinate system on the sun, or my new coordinate system because I'm now moving. And for this calculation, this number comes out the same. You never have to assume which coordinate system. It was highly surprising. How can you define velocity without saying with respect to what? And Maxwell's equations do this, with this number coming out. And everybody was thinking, well, how does that work? Maybe Maxwell's equations are specific to a very particular coordinate system. So maybe there's this one special coordinate system with respect to which this holds, and every other coordinate system is just wrong. Historically speaking, that coordinate system, it doesn't exist, but it was called the ether. A special coordinate system means Maxwell's equations are true. Okay, but Einstein, very young man at that moment, early 20th century, 1905, said, you know what? Maybe every coordinate system there's no special coordinate system, every coordinate system works. And the fact that this number comes out the same must be a consequence of physics itself. This is a special number, a special velocity in physics that is true for everybody, no matter which coordinate system they are. Now this idea, and it was extremely radical, it's still complicated, some people still struggle with it. This is indeed what you called the invariance of the speed of light. So Einstein, knowing electromagnetism, saw that this came out. By the way, other people had seen this too, but Einstein said, you know what, I'm going to not say there's a special coordinate system. I'm going to say every coordinate system is fine, and that the number comes out to say that's just a new property of physics. Now this idea that comes out, that was 1905, that was Einstein's famous paper. It's called the principle of the invariance of the speed of light. Apparently some new rule of physics. The speed of light, no matter who you ask, no matter in which coordinate system they themselves are, it's always the same number. We have to harp a little bit on the word invariance here. I think a second ago you said constant. That's a term. Invariance is also a term. They mean slightly different things. Constant, if a number is constant in physics, we mean that it doesn't change in time. If you measure it now and you measure it an hour later, the number is still the same. That's constant. Invariance, and we're going to use this word a lot, means something else. That means the same number, not in time, but between coordinate systems. So the principle, this is also something that sometimes in the books they misuse the language a little bit. They write down, oh, the speed of light is constant. Yes, that's true. The speed of light doesn't change in time. But the principle is based on the invariance. This idea, that the number comes out the same in all coordinate systems. So make sure that if you're making notes that you use the word invariance. We're going to use this quite a lot. The invariance of the speed of light. I will upload on Canvas the original paper by Einstein in which he does this. You don't have to read it, it's for supplementary material in case you're interested. And you will see that he indeed uses Maxwell's equations to get there. In fact, the paper, I won't try to say this in German, not to insult our German people in the room, because my German is bad. But in English translate, he wrote in German, he said the paper is called On the Electrodynamics of Moving Bodies. He says, if I take electrodynamics, this stuff, seriously, and I look at different coordinate systems, inertial systems, moving bodies, then this is my conclusion. So I will upload that for you to go through if you want. And it's here where relativity starts. That's the historical route. Because it has consequences. If things, or the speed of light has to come out the same for everybody, then distance and amount of time cannot be the same for everybody. Let's be very specific about this now. Let's say there's a car driving in that direction, and I want to measure how fast that car is going. And let's say it's 50 kilometers per hour. By this, I by definition mean that if I wait 1 hour, then in my coordinate system that is painted on the floor here, if I wait 1 hour, then it will be 50 kilometers ahead. Yes? Okay, fine. Okay, but now I start walking behind the car, and I do this myself at 20 kilometers per hour. Then in my new coordinate system, right, I drag a new coordinate. I'm not measuring with respect to the floor anymore. I'm measuring with respect to myself. The old system, the floor and me, now have a velocity of 20 kilometers per hour. If I now walk past that same car, in that same hour, in my new coordinate system, it will not have driven 50 kilometers away from me because, hey, I made up for 20 of those. It should have been going with 30, right? That's just what you would call Galilean transformations, how you would do physics before relativity. The word for that is Galilean transformations. Okay, well, that all makes sense. The velocity in my system, my new system, walking behind the car, is not 50 kilometers per hour, it's 30 kilometers per hour. Because in my frame, it travels 30 kilometers in that same hour. Now, who is right? Well, both of us are. The original me in their system says 50. The new me walking behind the car says, no, the car goes 30, and both of us are right. No problem whatsoever. What if I now replace that car by a ray of light? Then, if I'm standing still and that light car is going over there, then I will say, hey, every second it will go 300,000 kilometers. Okay. Now I take the next guy and their coordinate system, let's say that they go with 100,000 kilometers per second, moving behind the light car, and then they measure, well, how fast is that car going? You would think Galilean transformation, you would think, well, 300,000 kilometers plus 100 that I made up for that, so that light car should be going with 200 kilometers per second. No, if you ask the other guy, that's what this derivation tells you, that car will still be going with 300,000 kilometers. Well, that's strange, because didn't I just make up for the missing 100,000 kilometers because I was traveling behind it? So how did that happen? Why is the answer not 200,000 kilometers per second? I mean, the fact that this number has to be maintained, has to be invariant between the original observer and the new observer. The fact that that nature really wants this number to stay the same means that something must be different about the amount of meters that the car has, or the light has traveled, or the amount of seconds that the light has been traveling. You cannot maintain this number between inertial systems, keep it invariant, without changing the laws of space and changing the laws of time. The amount of distance and the amount of seconds must be different between me and the other guy chasing the light car. That's a direct consequence of this, and that itself is a consequence of the laws of electromagnetism. Now what we have to do is we have to find how they are different. Now, if we have those laws, so we're going to derive now a set of rules that tell me if my inertial system says the amount of time is so and so, that I can calculate how much the other person's inertial system, how much time it is in their system. We're going to do the same thing with space, the amount of distance. So let's do that now. What exactly are the rules that make sure the rules between this inertial system and this inertial system such that this number comes out the same always? And again, that's what Einstein in his 1905 paper figured out. Again, next week I will show you these rules in a way that has nothing to do with the speed of light or electromagnetism. I mentioned already at the beginning, there's much deeper reasons why this is true, but this is how it's historically done. That's also how our book does it, so that's why I'm showing you this. Including the way I'm going to show this now. And this might be something you have seen before, maybe in other books if you had it in high school, for instance. Right? Next week, we're going to see a much deeper way of doing it, but for now, let's go with the high school book version. Okay? So, how can you do this? Well, the idea is as follows. Let's introduce two systems. Let's take one inertial system. By lack of a better word, I'm going to call it system A. And there's another inertial system, and that's system B. Again, both of these are inertial systems by premise. By the way, what does it tell you about the velocity between system B and system A? If I tell you that both of them are inertial systems. So there's a velocity in between them, but is the velocity constant? Could it be an acceleration? Which one should it be if both of them have to be inertial systems? That should be a constant. So let's call that constant V, the velocity between this system and that system. If this was accelerating, remember from our starting thought experiment with my cart in the green system and the floor with the black system, then in one of the two systems, Newton's first law would not be upheld, meaning that one of them is not inertial. The fact that I make them both inertial means that they have to have a constant velocity with respect to each other. So that's this number. Again, if you're interested in how that works, if this is not constant, period 5, general relativity. Okay. Inertial system A, inertial system B. Now this is the way that the books typically do it. They do what is called, here's my German again, Gedanken experiment. They do a thought experiment. That means they say, well, suppose that this and this would be the case, and let's figure out logically what then the result would be of that. Okay? Now, what is the thought experiment that they do? They say, well, let's put a light bulb on the floor. That's typically how it's done. And they say, you know what? I'm going to shoot a light ray up to the ceiling. There's a mirror on the ceiling. The light ray bounces back. And I'm going to measure how much time it takes for the light ray to have made the full round trip, up, down. And we're going to calculate what that amount of time is for some observer in the A system. Inertial observer A. Let's say that the cart has a height of L. Yes? Now here's my high school physics. How much time does it take for the full round trip? You ask this person. So this should be the least difficult.
2L divided by C.
2L divided by C. And by the way, that special number, 300,000 kilometers per second, we've given the number, assigned the symbol C to. So we're going to use this. This is high school physics, right? The amount of distance that has to travel is 1 times up, that's L, times and time will go back, that's 2 times L. How much time does it take? If you know that the thing goes with the velocity that we call C, then it must be 2L over C. Okay, all fine. Now we're going to ask the same question to a person who is in the B frame. And now things are different. Because in the B frame, the light ray in their coordinate system, the light ray will not go straight up. It will move in that direction. If you don't believe me, put me on a cart, let me throw up a tennis ball. In my own frame, it would just, go back down on my hand. But for you, it started over here, it ended over there. So if you would track the motion of the ball, it would be this triangle shape, right? It would go up, bounce against the ceiling, go back down or so. Same here. So for them, the round trip is this amount. And now we have to calculate, well, how long does it take for that guy to see the light ray bounce up against the mirror on the ceiling and then bounce back again. Well, it's a bigger distance now, because it's not just this anymore, it's that distance, and that's bigger. And it has to go back still. So we might end up with a bigger amount of time. Let's calculate it. Well, first of all, let's first immediately observe that if we know how long it takes for the light to start at the light bulb, then hit the ceiling in the B frame, that's this amount, that if we know that amount of time, the backward track is the same amount of time, right? So we just have to do this exercise once, so to say. So we're going to take whatever time it takes for the light for this guy to see to start here, end up at the ceiling, and whatever number comes out, we're going to do times 2. Then we get the total amount of round trip time as seen by the B observer. Okay, well, what's the distance? This one. What's this distance? That's L, right? That's how high this guy is up. Well, what's that distance?
Velocity times time.
How much is that, sorry?
Velocity times time.
Yeah, exactly. It's the... it will be this, right? D times... oh, sorry. I'm just messing up here. Yeah, so this amount is how much the train cart has been moving forward while that first half of the trip was going on. Well, how much did it go forward? Well, how fast the train was going times the amount of time it was going. That means that this number over here, by Pythagoras theorem,
Shouldn't it be half time?
what's that?
Shouldn't it be half of the time?
Yeah, that's true. This is only for the half trip. You're right. So let's put 1/2 there. Would that be okay? So the 1/2 means half of the trip. Whatever number comes out, we'll do times 2. But thank you. Okay. So we know how much distance this guy says that the light ray has to travel. That's not this number. That's not that number. But by Pythagoras theorem, it's that number. Okay. Plug that in. V squared delta t b with 1/2 plus L square root, and divided by how fast the light ray was going. Well, according to the principle, it should still go with C. Note, had this principle not existed, the speed of light, the speed with which it was moving in this direction would be different also. Because you would say, it's how fast the light itself is moving, yeah, plus how much the train also gave it extra speed. But the principle says, no, it's always the same number, that number being C. So that's that number. And there's an L squared. Thank you. So in principle, we have the number now. Well, actually, the number that we want, so again, the 1/2 means half of the round trip time, is, well, it's on both sides now, yeah, you have to pry it out. But I think if we use our high school mathematics, we should be able to do that exercise, yes? So let's square both sides, then put a c squared over there, equals v squared delta t b squared 1/2 plus L squared, same thingy. I get a c squared minus b squared delta t b 1/2 squared equals L squared. I think I'm still correct. And that by itself tells me that the half of the round trip time, that's this number, is given by L over C 1 minus V over C squared, square root. I just pried the delta TB out using some high school algebra here. You get that number. So, if you're going to ask, well, how long did it take for the light to go from floor to the ceiling? This guy will say L over C, and this guy will say actually it's L over C plus this extra thingy over there. Yes? But we already agreed this is only half the time, and if you want to compare it to the full amount of time, you have to multiply by 2. So that means the full amount of round trip time is just that number times 2. I get 2L over C, 1 minus V over C squared, square root. And yeah, I can actually relate these two numbers to each other. Because this number over here is exactly what the guy in the other frame said that it took. So combining this amount and that amount all together is going to leave me with the relationship between the amount of time that is measured by the A person and the amount of time that is measured by the B person, delta TB. So how much time passed on this guy's watch as he saw the whole process take place is actually given by this number. That's how much time the other person says that it took, plus an additional factor, this factor. There's a special name. It's called gamma. So for completeness, and we write it out here, gamma is 1 over 1 minus V squared C squared square root. this number, and we will use it very often. It's called the Lorentz factor. It's the amount of difference between the time as measured in one frame versus the amount of time measured in the other frame. That's what the Lorentz factor stands for. As the course progresses, we will see that it stands for a whole bunch of other physics too, but for now in this derivation it simply means the amount of difference between those two people's times. Well, clearly that's not the same number. Delta TB is not the same number as delta TA. Right? There's a gamma in between. And how much time difference, how much Lorentz factor there is apparently dependent on how are the two inertial frames, in my example that's the train and the floor, how fast are they moving with respect to each other? It's V dependent. If V happens to be a very small number, that means the train is not moving too fast. And what I mean by that is compared to the speed of light, right, V over C tends to be a very small number because C is very big, 300,000 kilometers per second. Well, trains don't move with that speed at all. I don't know what they go, 180 kilometers per hour or something like that. That's a lot smaller. And the square of that is even smaller still. So in everyday examples, V over C, the difference between your frame and whatever other guy's inertial frame, be it a train or something else, V over C tends to be a very small number. And that means that this is very close to 0, and you just get that delta TB is up to 10 decimal points or so equal to delta TA. Right? That's why when you jump on a train, you don't have to worry about you being out of sync with the rest of the universe. Trains don't go fast enough. So that's what you see from this Gedanken experiment, this thought experiment. This is what we already foreshadowed when we saw from Maxwell's work that the speed of light is invariant, that the amount of time cannot be the same in different inertial systems. They have to be different. And we have now found one of the rules that makes them different. There's more. This is only one of them. Yes? It's one of the key ones of this week. You can do a same thought experiment, and in the book and in the notes you will see that written out as well. I will briefly mention how it goes, but I will leave it up to you to read or do the thought experiment yourself. Is that you can also ask, well, how wide is the cart actually? Not how high, how wide is it? Between what the A person says and the B person says. How can you figure that out? Well, one way is that you take this guy and he shoots a laser beam, but in this case not up, but forward. And then you measure how long does it take for that laser light to bounce back and forth and reach him. That amount of time tells you how wide the cart is. So this guy can measure, well, how big is my cart actually? But you're shooting a laser light back and forth. If you ask this guy, how wide is the cart? To him, that laser light runs into trouble, because as the laser light is moving forward, so is the train. So it takes slightly longer for that laser light to hit the forward part of the cart. Then it bounces back. Then it takes less time, because as the light is traveling towards him, he is himself traveling towards it. That takes a small amount of time. And then you can calculate how much time it takes for this guy to see the laser light go back and forth. And he can calculate how wide the cart then apparently was. This is written out for you both in the book and in the notes that I will share with you. But the answer I will tell you. The answer is that if you take the amount of width of the cart as seen by the A guy, there's also the same gamma in between. But now it's 1 over. Again, the derivation is very similar. You can read up on it in the book and in the notes. So, gamma, again, doesn't just mean how much time difference there is between inertial systems. That's this one. It also tells you, well, how much spatial distance is there between inertial systems. This formula, we're going to use this a lot, is called the Lorentz contraction. contraction literally means space squeezes in. And this formula is called time dilation. Time stretches out. It takes more seconds. And both of them are measured by gamma. Length becomes smaller with the gamma. Time becomes wider with the gamma. So gamma, if you want, is the relationship between space and time between the A and the B observer. That's what it says. Let's study gamma a little bit more. Let's draw gamma. Again, gamma is the difference between the amount of time and the amount of space. So we're going to draw gamma as a function of how fast are the inertial frames moving compared to the speed of light. If the speed of light, well, it is very big, but if the difference in, the velocity of the cart is very small, V over C becomes close to 0. Well, let's plug in close to 0 in the Lorentz factor. You will see that it becomes 1 over 1-ish or so, very close to. So there is no velocity between two inertial frames. The amount of gamma-ness is 1. And actually it stays 1 for a very long time because of the squaring. You have to put in an enormous amount of V to compensate the bigness of the C, and the square makes it worse. So you really have to go very fast in order to see it. And it stays close-ish to 1. It slightly rises up, but very small. It closely stays to 1 for a long time, except when you get close to C itself. And then all of a sudden, it flies up. How much does it fly up? Well, just plug it in. If V equals C, so the train and the other observer have a velocity that actually is the speed of light, then it becomes 1 over square root of 1 minus 1, that's 1 over 0, that's infinity. That's this. And all of a sudden it goes really fast. And I think all the way in the beginning, Max, I think it was you, right, who said that if you go very close to the speed of light, all of a sudden strange things happen. Well, that's what you see here. That's what the gamma factor tells you. As long as your velocity is relatively small, you don't see any difference. LA is about the same as LB, delta TA is about the same as delta TB. But if things really start moving fast with respect to each other, all of a sudden the amount of difference in space and time becomes extremely noticeable. So that's one thing that you can see here. One other thing that you can see from the Lorentz factor, just from the formula, is that, well, what happens if you go faster than light? Suppose that you take a cart that goes faster than light. The velocity between the two frames is bigger than C. And some of you might now say, but you cannot go faster than C. Because maybe you know, maybe you read it, it's true. But we haven't shown it yet. Right? That's for later. But you can already see that if you approach C, then things become strange because you go to infinity. But if V is bigger than C, then you get the square root of a negative number, makes it imaginary, as in imaginary numbers. That means if you would have a cart, a train cart that goes faster than the speed of light, then all of a sudden somebody's time is normal, the other person's time is an imaginary number. That's a bit weird. How does one measure imaginary numbers on your watch? Crappy. Same with distance. So you can already sort of see from this formula, maybe you cannot go fast on C because all of a sudden your watches give you answers that you don't know what to do with. It's not a proof. The proof we will see in a few weeks. But indeed, you cannot go faster than C. So this situation will not happen. And it's not because we haven't found motorized carts yet that go with the speed of light. We haven't, but that's not the problem. It's not a practical problem. You will see later in the course that it's actually physically impossible. The rules of space and time conspire against you, that you cannot go faster than C, no matter how hard you try, no matter how efficient you make your motors, no matter how much energy you use. We will see that later. So this problem will not occur. We will always be on the left-hand side of the barrier, so to say, in our exercises. Okay. Question. Whose time is bigger? Who measures the biggest amount of time? I drew the picture of the Lorentz factor, so the B, right? Because you take the amount of time for A and you multiply with something that's 1 or bigger. So if you ask this guy how long did it take to see something happen, in this case the laser light to go up and down, he will say, oh, I don't know, 2 seconds. Well, it will be very high cards, but you see the point. Yes. Small amounts of time. Then this guy says, no, actually, when you ask me, I'm not seeing that it took 2 seconds for this process to happen. It took, well, it depends on V obviously, but let's make it 5. That the gamma is 2.5. Here-ish or so. Yes? That means that this person will say that according to his watch, it took 5 seconds to see the light go up and down. So, whose time is running faster?
The one on B.
Yeah, the one on B, because in the time that it took person A to get 2 seconds older, sure, it was laser light going up and down, but it's the same amount of time that occurred on his clock. For the person A to get 2 seconds longer, or older, this guy became 5 seconds older. So what we've done here is not just an exercise in, well, how long does it take for light to go up and down? It literally means that this person, or this person, is not aging as quickly as this guy is. And by this, I'm not making a biological statement. Time itself is running slower in this frame than it is in that frame. So, let's make it concrete. Let's put myself over here. Without asking, I'm guessing most of you are about 20 years younger than me. Okay? But I put all of you guys over here. I happily going to be on that track. You make either a gamma big enough or I travel for long enough. And every time that I age a year, you guys age 2.5 years. So 2 years later, I'm only 2 years old, you guys are 5 years older. Go on, so on, so forth. At some point we stop the experiment, I jump out of my train, and poor you guys are older than me. That sucks. Nobody got younger, by the way. Well, all of us got older. I just got older less fast than you guys. That's not a statement about biology, it's not a statement about lasers, it's not a statement about trains, it's a statement about time itself. Time actually slows down if you move with a high velocity. That's one of those effects. Also, while you are observing me as we're traveling, or I'm traveling on the train, and you guys on the platform are watching me, something happens to my physical dimensions. What happens? Please.
You look like a stick.
I look like a stick, yes. Because you're right. So let's make this my width. Yes. And the way that you see my width is going to be, well, what I think my width is, divided by something that's bigger than 1. So you guys are actually going to see me shrink inward, so to say. Not if you ask me, I don't notice anything. If I have my homeboy over here, moving along with me, he and I don't have a relative velocity. So he would just see me as my usual width, so to say. So that's the Lorentz contraction. So what can we conclude from all of this? Just alone from Maxwell's equations and the invariance of the speed of light and doing this thought experiment, what we've concluded now is that if something moves quite fast enough to end up in this domain of the Lorentz factor, their time will go slower and their width will shrink. Lorentz contraction and time dilation. These are these 2 effects. All right, so to close off, a few finalizing comments here. One of them is that you have to be ridiculously careful if you're going to do exercises, and Brecht and I will go through some of these exercises using only these 2 formulas. You have to be extremely careful if you're going to have 2 observers, one person in a spaceship, one person in a not spaceship, and they have a high velocity with respect to each other. You have one person's time, calculate the other person's time. Okay, then you know that this formula holds, but where does the gamma go? Who's the A person, who's the B person? Right? In our experiment, thought experiment, it was clear, just following the math, the gamma ended up over here. But that's because we went through the experiment. If I just give you an exercise with two things that are moving with respect to each other, well, who gets the gamma, so to say? Whose of the two times gets a gamma in front to get the other person's time? Yes?
The person in whose frame of reference the location of the event doesn't change.
That is absolutely correct. Thank you. I've seen this very often, that people sometimes even randomly place a gamma in hopes of getting the right answer, so to say. No, there's more to it. Where does one place the gamma? You have to place the gamma. Well, let's take one step back. The first thing you do if you do an exercise is that you have to find out if you have two things happening. In this case, that's the start of the light journey and its return, because that's the amount that we're measuring by our delta TA. That you have to figure out, is there an observer who sees the starting point of whatever happens and the end point of whatever happens? Do they see the same location? Here that's clearly the case. That's person A. The start, the position of where the light started in his own frame and where it came back is the same location for him, namely at his feet. Yes? That person is the one whose time gets a gamma in front. The other person, person B, does not see the start of the process, the start of the light journey. And the end of the light journey happened at the same location because it started over here, but as the light returned to the floor, the train was all the way over there. So the return of the light happened all the way over there, not the same location where it started. That's the person who ends up at the other side of the equation. You have to be extremely careful for this. So, when we're going to do exercises in tutorials, Brecht and I will pounce you that you start every exercise with saying, okay, what are the two things happening? Write them up. Then figure out for whom those two things happen at the same location. And then you start writing formulas because then you know where the gamma goes. Yes? We have a special name for that person who sees the start and the end of a process happen at the same location. It's not TA, we call this the Greek letter tau. This is ubiquitous. You will see this in all works on relativity. So what is tau? Tau is the amount of time as measured by a person who sees the start and the end of a process happen at the same location. It's called the proper time. We'll use that word very often. Equally so, if you want to use the formula for Lorentz contraction, well, who shrinks and who doesn't, same thing. The person who sees the two things happen at the process happen at the same location has a special symbol. It's called S. It's called the proper distance. I'm not telling you any new physics. I'm simply introducing the terminology that hopefully will help you. I know it's now filling the rest of the group. So, yeah, everybody wave. Clearly, some kinks have to be figured out. It's AI. Apparently, it has an AI me or somebody around this looks suspiciously like me. I'm not seeing anyone. If only you were so lucky. We'll figure out the kinks.
It's
Oh my god, yes.
Oh my god.
A new professor.
Yes.
I have a question.
Yes.
Another question. You said the proper distance is measured by the person who measures at the same position.
Yes. Yeah, I misspoke. Thank you, Bert. So the delta S, right? The proper distance. If I'm pedantic about this, but thank you for the question, is if you want to measure a distance, what you typically have to do is locate first where one side is of the thing, and then you locate where the other side is of the thing. You have two numbers and you subtract them from each other, right? That's how you measure a distance. Okay. But if you're going to ask this guy to measure this card's distance, and you first measure where the end point of the card is, and then you wait 2 seconds, and only then are you going to measure where the front end of the card is, and then you're going to subtract those two numbers. You're not going to get the correct number for the distance because it was moving in the time that you were waiting. Yes. So if you want to measure a distance, and you're not standing still with respect to the thing of which you are measuring the distance, you better be sure that you measure front end and back end at exactly the same moment in time. So, thank you for that question. What is a proper distance? It's the amount of distance measured by somebody who measures front and back end at the same moment in time. I think that's in place. Thank you. Okay, final thing. This is not complete. These two equations that we have over here, the Lorentz contraction and the time dilation, assume that there is one person who sees things happening at the same location, right? That's how you identify who measures proper time. Or, thank you for the question again, or that there is one person who sees a process happen at the same time. But you can also have observers for whom neither of the two is the case. They look at something happening, be it a laser light jumping up and down or whatever takes time or amount of distance, for whom the two locations and the two moments in time do not happen at the same position or the same time. Then neither of these two equations are correct. This assumes one observer sees something happen at the same location and the other observer sees things happen at the same time. If you have an exercise where this is not the case, none of your observers obey that rule, then these equations do not work. So next week, we're going to derive a fuller set of equations that hold for all cases. But that's for next week. So, to wrap up, Bert and I are going to do a couple of exercises with these with you. I stress what we did now is a derivation based on history, on the electromagnetism. Next week we're going to see that even if you leave electromagnetism out, you can derive all the same rules without Maxwell's equations, and you will find that there's a much deeper and richer structure. But that's next week.